Today we're going to talk about the qualitative implications of impulse. So we addressed one of these already when we were looking at the quantitative implications of impulse. We talk about impulse as the change in momentum experienced by an object. And we know that when an object is stopping, it experiences an impulse that is predetermined. That impulse is not affected by how it stops. We talked about that in one of our sample problems and in a number of the problems that you will work on in class. An object falls. It's going to hit the ground and it's going to stop. No matter how it stops, it will experience the exact same impulse. A car traveling down the highway, it's going to stop eventually. We know what its impulse is going to be. It's traveling down the highway at 110 kilometers per hour. Its impulse is mvf minus mvi, 0 minus mass times 110 kilometers per hour. The impulse of an object that is stopping is going to be the same no matter how it stops. But we also watched a video yesterday before we did the activity. Remember the ledge jumper video? Guy jumps off the ledge, jumps onto this air pad. Nothing happens to him. Why does nothing happen to him? Well, he experienced the exact same impulse when he hit this air pad as if he had to hit the ground. Why did nothing happen to him? Because that impulse that was predetermined by how high he jumped from was spread out over a longer period of time. What does that do? What does that accomplish? What benefit is there to that? It decreases the force, right? When you have a predetermined impulse, an impulse that is going to be the same no matter how the object comes to a stop, the idea is almost always that we want to increase the stopping time, which is going to decrease the force. So, first situation here, we'll say we have a predetermined impulse. You guys write that down when you read it through here in a couple of days. Well, you know what I mean by that, a predetermined impulse? An impulse is the same no matter how an object is stopping. We'll put here in brackets, object is stopping. Delta P is equal to F times T. The idea here is that if the impulse is predetermined, it's not going up or down. If we increase the stopping time, we're going to decrease the force. Now, is there a situation where maybe we want to do the exact opposite? We want to decrease the stopping time and increase the force? Maybe. Maybe if you want to destroy something, sure. But almost always, the idea is to increase the stopping time, which is going to decrease the force. That is, as we said yesterday, the basic principle behind every impact cushioning device out there. Everything that cushions an impact is based on this principle. Goalie gets hit by a puck. What happens? Well, it doesn't hurt him so much because he's got enough padding on that we increase the stopping time of the puck, which decreases the force. Basketball player catches a basketball, brings his hands back like this. The idea behind that is that he increases the stopping time of the basketball, which decreases the force on the basketball. You stand on your desk and you jump off your desk onto the floor. When you do that, you bend your legs when you hit the floor. Why do you do that? Because intuitively you know that if you increase the stopping time of your body when you hit the floor, you're going to decrease the force and it's going to hurt less. You always see, in movies, when guys jump out of a moving car, what do? They roll. They don't just try to land on their feet. They kind of land on their body and kind of roll. What's the idea there? Well, let's not stop right away. Let's not stop immediately. Let's increase the stopping time, which is going to decrease the force. Okay? Every single time an object is stopping, increasing the stopping time will decrease the force. Now, what's the other scenario? Well, the other scenario is when, if we have a predetermined impulse in number 1, we have a non-predetermined impulse in number 2. I don't even know if that's a word, by the way. A non-predetermined impulse. I don't know if it's a word, but we're going to say it is. In the end, what I mean by that is an impulse that is not determined by its initial conditions, an impulse that can change. An object experiences a non-predetermined impulse typically when the object is starting as opposed to stopping. Who's a golfer here? Anybody a decent golfer? I go golfing once or twice a year. If I do that, if I go beyond once or twice a year, I find I get really bad. It's kind of weird, actually. I do okay if I go once or twice a year. If I go 3 or 4 times a year, I just start going downhill, and I start getting depressed. I'm not a very good golfer. If I hit 100, I'm happy. On 9 holes. No, on 18 holes. Those people who golf know that, at some level, know that the impulse of the ball, the momentum of the ball, is not predetermined. You want to give the ball as much impulse as you possibly can. Why? The ball's sitting there on the tee. You want to give it as much impulse as you possibly can because you want that ball to go faster and you want that ball to go farther. The initial conditions of that ball are mass of whatever, a velocity of 0. You control how much impulse it receives. Hockey puck is the same thing. You control how much impulse that hockey puck receives when you shoot it with your stick. Baseball, okay, you swing the bat. You control how much impulse the ball receives because you're starting it moving. A car that's sitting at a stop sign. You put your foot on the gas pedal, you control how much impulse that car receives. That's not a predetermined impulse. Okay, we're affecting the amount of impulse that it receives. What's the idea behind a non-predetermined impulse? Well, what typically happens there is we want to usually we want to maximize impulse. And to maximize impulse, we can do 2 things. To maximize impulse, we can increase the force. Think about that. If you want delta P to be bigger, then let's make F bigger. If you want the golf ball to go farther, hit the golf ball harder. If you want the car to go faster, then put your foot down on the gas pedal more. If you want the baseball to go over the fence, then swing the bat harder. Apply a bigger force, give it more impulse. But what else can you do? Here's the difference between a really good golfer and someone who's not a really good golfer. It's not the force. It's part of it, right? But the real difference between a good golfer and not a good golfer, or a good baseball player and not a good baseball player, is this. If you increase, not the stopping time, because we're not stopping. If you increase the time of contact between the golf club and the ball, or between the baseball and the baseball bat, or between the puck and the hockey stick, then you're going to increase the impulse. What does that generally boil down to? Follow through. When you hit a golf ball, you don't do this and stop the golf club as soon as it hits the ball. You follow through. What does that do? It increases the time of contact between the ball and the club. It increases the impulse. What do you do when you hit a baseball? Well, you don't just do this and stop the bat like that. You follow through. It increases the time of contact, which again increases the impulse. You got to hit it hard, big force, but you also want a big time of contact. Does that make sense? So we're stopping an object that has a predetermined impulse. We can't control it. We're starting an object where we do control the impulse. We're stopping an object. We want to increase the stopping time that decreases the force. We're starting an object. We want to increase both the force and the time in order to increase the impulse. Let's take a look now at the last thing that we do with impulse before we move on to our next topic. For the first time this year, you're going to see a graph today. The graph that you're going to see is a force versus time graph. If it's force versus time, then that means force is going to be on the y-axis and time is going to be on the x-axis. There are 3 words that I want you to automatically come to your mind when you see this force versus time graph. Those 3 words are the following: area equals impulse. I don't care what you're asked to find. I don't care if the question doesn't mention the word impulse or area once. I don't care if the question looks different than the last question you saw. As soon as you see a force versus time graph, I want you to automatically think area equals impulse, because you're going to do that every single time, regardless of what you're being asked to find. Now, there are a couple little things that we have to pay attention to. When we calculate the area above the x-axis will be considered to be a positive value. The area below the x-axis will be considered to be a negative value. So for instance, if we have a graph that looks like this, force versus time, again, we automatically think area equals impulse. But if part of that line is above the x-axis and part of it is below the x-axis, then we've got to calculate this area up here and make it a positive value. And then we've got to calculate this area down here and make it a negative value. If our final answer is positive, then we have a positive impulse. That means momentum was gained. If our final answer is negative, then that means we have a negative impulse, a loss of momentum. Momentum was lost. Now, every once in a while, you get one of these questions where they don't actually ask you to find the impulse. They ask you to find the change in velocity or something like that. We still think area equals impulse. We still get the area of the graph, get the value of the impulse. But then we set the impulse that we've just found, in other words, the area, equal to m times delta v. And then we just simply solve for delta v. So most times you're going to see this graph, you're going to think area equals impulse, and you're going to calculate the area to get impulse, and you're going to be done the question. Every once in a while, you're going to see an f versus t graph where you're asked for the change in velocity. You're still going to think area equals impulse. You're still going to calculate the area to get the impulse, but you're going to set that value equal to m times delta v, and then just turn around and solve for delta v. Does that make sense? One sample problem that we're going to look at today, obviously it relates to this. That example question is 9.4 on page 462 of your textbook. It says a golfer hits a long drive, sending a 45.9 gram golf ball due east. See what I've just done? Haven't even finished the question, have no idea what we're going to be asked, but I just circled grams because that's an area where I will often make a mistake if I don't draw attention to it. If I even use this number, it's got to be in kilograms. Figure 9.22 shows an approximation of the net force as a function of time for the collision between the golf club and the ball. What's the impulse provided to the ball, and what's the velocity of the ball at the moment the golf club and the ball separate? And when we look at this graph, automatically I should think three words. What are those three words? Area equals impulse. It doesn't matter what I'm being asked. In fact, as soon as you see this question, before you even read the information over there on the left-hand side, you may very well just think area equals impulse, or even write down area equals impulse to not forget that. I want to circle this as well because I'm in milliseconds. Okay, that's not real common, but it happens, where we see something that's non-standard units on the graph. Milliseconds is 10 to the minus 3. So whenever we see, say, 0.6 milliseconds, that would be 0.6 times 10 to the minus 3 seconds. And of course, if I'm going to do a calculation with this graph, I want to make sure I'm in seconds, not in milliseconds. All right. What do we do here? Oh, well, you know what? I'm not even going to look at question A and B again right now. Okay, not even going to remember what I'm being asked here. First thing I'm going to do is just find the area of this graph. Area equals impulse, because I know I'm going to have to do that. And that's going to help me with question A and B when I go back and look at that. So let's get the area of this. It's a triangle. What's the area of a triangle? This is like grade 5 or something, isn't it? Area of a triangle. Length times width divided by 2, or 1/2 base times height. Good? The base of this, it goes from 0.1 to 1.1, so the base of it is going to be 1.0, right? Is that right? No, it's not right. What's the base of it? 1.0 times 10 to the minus 3. That's why I circled that and wrote in the 10 to the minus 3 so I wouldn't forget to include the exponent there. The height of it goes from 0 to 5,000, so it's just going to be 5,000 newtons. 1/2 of 1 times 10 to the minus 3 times 5,000, I think just gives me 2.5, doesn't it? What are the units that go along with that? Area equals impulse, so the units would be either kilograms meters per second or newton seconds. Now, go back to the question. It says, what's the impulse provided to the ball? Already got it done. 2.5 newton seconds. Question B is a bit tougher. It says, what's the velocity of the ball at the moment the golf club and the ball separate? Let's look at this graph for a second and see if we can figure out where it is that the golf club and the ball separate. How many people think, hands up, okay, when you have an answer to this. How many people think the golf club and the ball will separate right here at position A? It's not where they separate, is it? That's where they come together, isn't it? How many people think they're going to separate right here? Okay, quite a few. How many people think they're going to separate right here at position C? Okay, so it's about half and half between B and C. The golf club and the ball are going to separate right here. Let's think about that. Can the golf club apply any force on the ball after it's left contact, after it's not touching the ball? The golf club doesn't apply a force on the ball after it's not touching, right? Here's what happens. The golf club, you guys saw the Phil Kessel hockey shot video just a couple minutes ago. Okay? As you're shooting, the golf club or the hockey stick, whatever it is, flexes. That increases the force. It's Hooke's law, right? F is equal to kx from physics 20. As it bends more, the force is bigger and bigger and bigger. And then what happens? It starts kicking back, and the force becomes smaller and smaller and smaller. But it's the puck, or in this case, the golf club, still hasn't left the club until this point, when the force is 0. So, what's the velocity of the ball at the moment the golf club and the ball separate? We're analyzing the entire graph again, not just half the graph. We're going to use the impulse that we just got in question A, and we're going to set that impulse equal to m times delta v. Delta p we already determined is 2.5, and the mass here is 0.045 kilograms. I'm not going to forget to convert that to kilograms because I already circled or highlighted or underlined or whatever the grams. When we do the math on this, we end up getting a change in velocity of 55.6 meters per second. So the golf ball presumably was at rest, and now it's going to be moving 55.6 meters per second. That's the change in velocity. How could we make this question just the tiniest bit harder? Well, let's say the ball doesn't start at rest. Let's say it's a baseball problem. Okay, the ball is moving towards us. We want to find the final velocity of the baseball. Is that what we've just found? We found the change in velocity. If there was an initial velocity, how would we find the final? All we do at that point is say delta v is equal to vf minus vi. We'd have delta v because we solve for it that way, and presumably we'd be given vi, which would allow us to solve for vf. It doesn't make it that much harder, but it makes it a little bit harder. All right? You guys feel okay with that? Good enough to try a couple questions? People are thinking, how do I respond to that? I don't really want to do the questions. So if I say I'm not good with it, is he going to make me do the questions? Yes, I am, after we do another example. You guys okay? Do we need another example, or are we good? Good? All right. Let's take a look at these two questions, please, on page 462 that go along with that example problem. Everybody take a look up here for a moment here. I just want to take a quick look at question number 2, not to do the entire question, but just to set it up for you. Then I'm going to assign a few more questions, then we're going to drop our eggs. Okay? Question number 2 says, we got a soccer player heading the ball with an average force of 21 newtons, and we can assume it says that the net force, the average force, is constant during the interaction. So the graph is going to look something like this. Force versus time. 21 newtons is up here, and it's going to go straight across for 0.12 seconds. Okay, the graph's going to look something like that. Pretty straightforward. Now, question B, we want to find the impulse. What are the 3 words we automatically think when we see this graph in front of us, this F versus T graph? What are those 3 words? Area equals impulse. So let's get the area of this. The area of this is going to be base times height, which is 0.12 seconds times the height of 21 newtons. And what do we get when we multiply 0.12 times 21? The answer is 2.5 newton seconds. 2.5 newton seconds. And since everything is to the west, then the area or the impulse is also going to be to the west. Now, question C, we have the initial velocity and the final velocity. We want to find the mass of the ball. We know the area. We know the impulse. We don't know the change in velocity, but we can find the change in velocity. Change in velocity is VF minus VI. VF is negative 2.0 because it's 2.0 to the west. VI is 4. So it's negative 2 subtract 4. And then we take that over to the other side by dividing. We end up solving for the mass. Does that make sense? All right, here's your homework for tonight. You can work on it during scheduled help because after we get out of the computer lab, we will be back here. The homework is page 467. Finish these up if you haven't finished them, obviously. But I also want you to do page 467, some check and reflect questions, number 1 to 13. 467, number 1 to 13. We'll check these over tomorrow. We'll have ourselves a little quiz on impulse on Friday. Impulse quiz on Friday. Tomorrow will be a quiz-free day. We'll just check over the homework and move on to the next topic. Make sure you've done these questions for homework, though, and let's be ready for that quiz on Friday. All right?